Bonjour, monsieur, madame. Je m'appelle David. Je suis noir. Oui, merci beaucoup. On a serious note, though, welcome to another AQA Electrochemistry video. Today I'm going to be doing a video on electrochemical cells, and it's starting a new unit. This is actually electrode potentials. It's not a long topic, or it's technically by unit numbers. The number of units is not a long topic, but it's quite a. I wouldn't say it's even a long topic to do. Like, it's quite a lot to understand when you first do it for the first time. I think the natural consensus of people when they learn this topic is they just understand it as electrolysis, and it has technically something with electrolysis, but it's quite a lot of new things that introduced that wouldn't make sense with your basic understanding of electrolysis. But anyway, I'm going to go straight into the video and talk about what this topic is about. This kind of starter topic. A lot of diagrams here, and a lot of new information that you need to take in. So if you want to take notes, do that, I guess. But there's no forcing you. And yeah, so electrochemical cells. So an electrochemical cell can be used to make an electrical current. A cell. So it's not the cell that you think about in physics where it's not the cell that you think about in physics where sorry, it is the cell that you think about in physics, but it's not by a basic level of understanding of cells where it's just all you have to know in physics really is just this, right? But really, in that battery, in that cell, in that unit, this is what's actually here. Sorry, I was thinking about circuit. A cell in physics, or the symbol for it is that. What's going on is this here, right? And so I've labeled it here. And this is what you need to understand. I'm going to go into more depth about more about the workings of it, but this is what a this is what a cell looks like, where you've got your electrodes, a voltmeter there, a salt bridge, which I'll explain what that is and why it's important, an electrolyte solution, and that's pretty much it. And it's joined together, and you have each solution or beaker here represents a half cell, and then the whole thing is a cell. The two of them together make a cell. So I'll go into more depth as to what this all is, right? So how is a current made? So there's two processes happening in a cell, oxidation and reduction. So one metal is being oxidized and gives up an electron, and in another side of the cell, the other metal accepts these electrons. So all there is a potential difference where there's a difference in charge across the cell, right? And all there is that the wire is just a think of the wires as a medium that allows that charge to move from one side of the cell to the other, where on one side of the cell, one side of the metal is oxidized and it donates electrons. So it'll be, if we're going from positive to negative, this side here is oh actually I don't use that. This side here is the positive end. It would oxidation there, right? That's not the technical term here, but I'm not going to use the exact set term here. But all I'm trying to say is that one side of the metal is being oxidized and donates electrons, and then the other side, this electron then travel across this wire, of course, and it gets to the other side here where it will be reduced or accept electrons. The electron travels from one side of the cell to the other via the wire, which is an electrical circuit. So this is what I'm saying of the electrical circuit, right? Electrode. So often you're using an electrode that's made of the same metal that are being oxidized or reduced, but you don't have to. And if one of your equations doesn't involve a solid being formed or lost, you'll need to use a different metal. And these circumstances, we use a platinum electrode because they're inert and don't tend to react with anything. Right, so oil rig. I mean, I think everyone knows about the simple mnemonic of oil rig. So on simple mnemonic of oil rig, which just means oxidation is loss and reduction is gain. It's just useful to understand that. Now I'm going to talk about half equations. So hopefully you got what I'm talking about here. If you're confused by this point here, I will actually I'm gonna. If you're confused by that, all I'm saying here is that usually you use an electrode we usually use the same electrode, or use two different electrodes. Actually, if you understand basic GCSE electrodes, you use one electrode of particular type of metal here, and then use another type of metal as another electrode here, right? And they have to have a difference a difference in reactivity series, right? That's usually your basic understanding of it, right? It gets a bit more, I'd say it gets more advanced in the understanding of it, but technically the method that you have to understand at A level makes more sense and it's easier to understand than the method that you understand in GCSE, where there's a table. Well, you guys need to understand something called a reactivity series in GCSE, but in A level you understand the electrode potential table, which tells you the different electrode potentials. What's an electrode potential? I'll go into that later, but yeah, but what I'm trying to say, you can actually use the exact same type of electrode on on the on the you can use two of the same type of electrode for your cell, but what you can change is the concentration of your electrolyte solution, and that can still allow for what I said here, for a current to be made where electrons will be traveling from one side of this. Well, one electrode will be acting as the anode, and the other one will be acting as the cathode, and there'll be free movement of electrons to the other side, going from the from the positive end to the negative end. But sorry, and now I'm sure you can understand that. But what you need to get is that if you're not forming a solid, you would use a platinum, and you just want to reduce a ion, but it's not going to form a solid. Obviously, because ions are only in solution, right? If you're going from a 4 plus or 3 plus ion to a 2 plus ion, it's still going to remain as a solution. You can use a platinum electrode because it's inert and it's a good conductor of electricity. So you can just allow for the free movement of electrons for to reduce or to oxidize those ions. So half equations and reduction potential. So you should understand what half equations are from GCSE, but if you don't have a good understanding of them, an ionic half equation shows either reduction or oxidation. That's all it is showing. It's just showing either oxidation or reduction. So for example, I have O2 plus 4 electrons goes to form 2 O2 minus. And that's let me write the 2 O2 minus here actually. It's this here, 2 sorry. 2 O2 minus. So O2 plus 4 electrons goes to form that, where oxygen is reduced to O2 minus, and obviously with two of those there. That's the type of half equation. So this is the ionic half equation for the reduction of O2 to 2O2 minus. If you have an ionic equation for the reduction process, which is what we have here, and an oxidation process. So say you have another half equation for the oxidation process of another type of reaction, you can then add the two half equations together to make one full balanced equation. And I want to highlight this part here because I think this is the biggest part of all of this entire unit. The majority of exam style questions based around this whole thing here regarding half equations. That's the majority of your marks, being able to understand how to rearrange half equations and how to form the half equations, and then being able to use your understanding of electro potentials and the half equations to make a full balanced equation, and being able to balance those equations and be able to know how to make an electrode. I forgot the name of the equation. A specific type of way of writing equations in electrochemistry. I forgot the naming of it specifically, which I should probably remember. But well, that's another video. I'll get onto that when I make that video. But having a good understanding of how to write half equations and then be able to know, based off the reaction that you have and based off the electrode potential, which I'll go into later, how to know which direction is reduction, which direction is oxidation, and be able to use that to make a full equation. Hopefully that was making sense to you. And if I'm not making sense to you guys, leave a comment in the video and I'll try to improve my videos. Criticism is useful for me. I probably the biggest one's probably I talk too much sometimes, but anyway, I'll just try and continue on. So reduction potential. So by convention, we write half equations in electrochemistry as reduction potentials. This means that we write half each equation with the electrons on the left hand side and show species gaining electrons. And we do this because each reaction is reversible. So in in electro potentials or electrochemistry, we represent our values as as reduction potentials. So basically, we don't ever show a reaction. Well, it doesn't really. We don't really represent it as, even the oxidation reactions. We still represent them in the reduction pathway form. And I said here, this it just means that we write each equation. We do this because the reaction is reversible. So we have a standard. Basically, what we're trying to do here is we're trying to create a standard. We don't want too much complication. We don't like saying one reaction here is the oxidation process, but it can change to be the reduction process based off of electropotentials. What we will have as a standard. So we're going to write all half equations in the direction of reduction, because that's what we're comparing a standard to. But if need be, we know that if we want to make it an oxidation reaction, we can just flip the reaction. And that's why it's so useful to represent them all in the reduction, because when you actually do this topic and actually try to make full equations, all of them will be written in reduction, but it's by saying that this one is actually going to be the reduction reaction, but this reaction, based off of, and I'll explain how you'll know which one is reduction, which one's oxidation, is something called electropotentials. I'll get onto that. Say this one has a higher value, so it's reduction, which means that the other one that they've highlighted me to look at must be the oxidation reaction, and therefore I just do the flip. I just flip the reaction round. If one way is reduction, the other way must be oxidation, and then be able to use that. Say these are two equations, and this is the two directions. So one's going from left to right, one's going from right to left, and I can use that to make our balanced equation. Now, understanding that can be very difficult to understand by this, and I'll be doing videos later on where I'll do an example to show you what I mean, because I can understand that could be very, very difficult to understand what the hell is he talking about, what's an electropotential, how am I going to know, how am I going to be able to make a full equation. Don't worry, the next videos or next couple of videos will be me going through exam questions and going to depth about electropotentials. But yeah, I'm going to continue on because I don't want to confuse you with too much and don't want to ramble on too much. So direction of change. So every reduction potential will have a quoted value for the electrode potential. This is measured in volts. So to say the electrode potential, if we write that little theta there is actually written like this, and the theta here actually represents this little theta here represents standard conditions of, and I'll go through the standard conditions, but this is this symbol here is used to represent the electrode potentials. And so every reduction potential, so every half equation, which is the reduction potential, will have a quoted value of an electrode potential, and we can actually measure that value in volts. So every half equation actually has an electrode potential in volts. So a positive electrode potential means the reaction is favorable. So if you have a positive electrode potential, it means that the reaction is favorable compared to the reduction of hydrogen ions. It means the reaction is, all that means is that the reaction is more likely to get reduced, which makes sense. If it's a positive value, it's more likely to gain electrons. That's how I like to think of them. If it's positive, it's more likely to gain electrons and is therefore more likely to be reduced. And the more positive it is, the more likely it is to be reduced. Vice versa. A negative electrode potential means the reaction is not favorable compared to the reduction of hydrogen ions, i.e., it means that a negative electrode potential means the reaction is favorable to the oxidation of hydrogen ions. It means the reaction is much more likely to be oxidized, which makes sense because if you have a negative value, it's more likely to lose electrons than gain electrons. You're more likely to be oxidized than to be reduced. And the more negative it is, the more likely it is to be oxidized. And this understanding of this is very, very, very important into allowing you to answer some of these questions for writing full equations based off the reduction potentials you have. Because as I said before, they're all written in reduction, but it's about having a good understanding of your understanding of reduction potentials to say, though they're all written in reduction, the direction of reduction, this reaction will be oxidized. If I were comparing these two reactions, this reaction here, which has a negative electron potential, is more likely to be oxidized compared to this value here, which has a more positive electron potential. And then you can use that and say flip the arrow to make them go to make the one that's going to be oxidized go the other way, and say, okay, now I have all the information here. I can now make a full equation. I know I said that a couple of times, but these key things here is vital for your understanding of electron potentials. This is just an opener video, but as I'll be going through how to answer these questions later on. But yeah, I just want to make up one key thing here. So I'm going to go on to the next part here, which is the standard hydrogen electrode. So I kept on saying here when I was talking about this little key factor about the reaction, if it's a positive electron potential, means the reaction is favorable compared to the reduction of hydrogen ions. But I said compared to the reduction of hydrogen ions. But why do we compare them to hydrogen ions? Now, we need to have a reference. How can we say one value is more positive than the other? We need to have a reference, and the reference that we use to say that this is more positive than the other is hydrogen ions. So the standard hydrogen electrode, so the way we're able to measure the standard the electron potential of hydrogen is by something called the standard hydrogen electrode. In your exam, it'll be actually written as she. You know, why does it keep doing that? It'll be represented by it like this. Sometimes, not all the time, but sometimes you see that. That's just all it means. Don't get worried about it. It's just called the standard hydrogen electrode. Now, I should have probably got a better example instead of just drawing it out. But I think I did a pretty decent graph. I think I drew a pretty decent graph. Anyway, I'm not going to try and admire my graph too much, but the standard hydrogen electrode is used to measure the reduction potentials. A reduction potential, I said reducation potential, that's completely wrong. Yeah, a reduction potential can't be measured alone because the reduced species needs an oxidized species to lose electrons to allow a current to flow. To solve this issue, we use standard hydrogen electrons. So as I said before, so as it says here, you can't actually just measure a reduction potential because as I meant all the way back up here, how is a current made? You actually need a potential difference for a current to be made. You need to have a difference in charge. You need to have one side of the metal being oxidized and to give up electrons, and then on the other side the cell, the metal can be the other metal accepts these electrons, right? So you can't just measure the rate of reduction by itself. You need to have both a reduction and oxidation process, right? So how we solve this and how we're able to create the standard of measuring that standard hydrogen standard hydrogen the electron potential. So how we're able to create a standard by finding out the electron potential of hydrogen reduction is by using something called the standard hydrogen electrode, and measures the reduction potential, and it's pretty much this apparatus here. You need to know what this apparatus is. You need to know this apparatus here, right? Which probably shouldn't be too difficult for you to know, but you also need to know about this apparatus here. You don't need to know about the dome too much. There is a reason for it. I don't believe you actually need to draw out the dome. Don't worry about that. But you do need to know what this little mechanism here with the platinum and the beaker, the electrolyte solution, and the actual standard values. But this is just I'm just saying here that to solve this issue of the issue I mentioned regarding you have to have an oxidation and reduction process. We have this standard hydrogen electrode, and it allows for because the reduced species needs an oxidized species to lose electrons and to allow current to flow. This solves that. We use the standard hydrogen electrode to do that. It allows for reduction potential. It allows for a reduced species to be sorry, I lost my foot in there, sorry. It allows for oxidized species to lose electrons, uh, and those electrons would then flow down, sorry, via current across a wire to a reducing species, to a species that needs to be reduced, right? And that's what we're allowing here, right? And this is the apparatus here, where we have a wire, and this will be connected to some sort of circuit, and that's we have a voltmeter here somewhere, right? All that nice things, all that, but we allow the current to flow down, and we actually have this dome here. We have a solution of H plus, which is just acid, and this when we're allowed to have 1 mole per dm cubed of that acid. Standard temperature of 298 Kelvin, but this apparatus here actually allows for hydrogen reduction. Now, the standard hydrogen electrode, the important features of a standard hydrogen electrode are that it has to have a pressure of H2 gas at 100 kilopascals. So standard pressure of 100 kilopascals. A H plus aqueous concentration, so 1 mole per dm cubed solution of acid. So if you have, so this, actually I'll go back onto that one. And then the last one is temperature of 298 Kelvin. So these are the standards. Right, 100 kilopascals pressure of H2 gas, concentration of 1 mole per dm cubed of acid, and a temperature of 298 Kelvin. So the 298 Kelvin one is the one you probably everyone would probably accept to be standard. But one people don't realize is that 1 mole per dm cubed of acid was not 1 mole per dm cubed of, I say 1 mole per dm cubed of acid because that's what H plus is, right? But it's specifically 1 mole per dm cubed of H plus concentration. So if you have 1 mole of HCl, right? So if I have 1 mole, sorry, no, 1 mole HCl, that's fine. It's fine to have 1 mole per dm cubed of HCl. That's fine. But if you had, that's that because HCl is a strong acid, you'll accept that. But what you can't have is 1 mole per dm cubed of H2SO4. Because you know that H2SO4 is a strong acid. H2SO4 is a strong acid that would dissociate 2 H plus ions. So you'd actually get 2 H plus. You realistically, that's what you're really getting. Of course, you're getting the SO4 2 minus ion, but the sulfate ion is a spectator ion. Doesn't really get involved in any of the reactions. But the 2H plus here, that's double, and that's no longer standard conditions. Now we have technically 2 moles per dm cubed of H plus here. So what you'd actually do, if you can use H2SO4, that's fine, but it would have to be half a mole per dm cubed H2SO4. And the same thing would be applying if you had H3PO4, where you'd have to use a third mole, I guess, a third mole of H3PO4 or phosphoric acid. Now, phosphoric acid, that's the own thing, but the point being here is being able to understand that you have to have 1 mole per dm cubed of H2 of H plus aqueous in your aqueous solution in your beaker. And so why do we need to do this? So as I said before, why do I need to do an standard hydrogen electrode? Like, why do I have to set up this apparatus? Is because we can only measure an electrical potential if a current can run, and we need one species to accept electrons and one to donate electrons. Therefore, we can't measure the electrical potential of a half equation by itself. We can only measure of a full equation. And we have to measure the electrical potential relative to the electrical potential of something else. And we define the electrical potential of the standard hydrogen electrode to have an electrical potential of 0 volts. So that's a standard. This is a standard that you need to know for exams. The electrical potential as a standard that we use, the electrical potential of the standard hydrogen electrode is 0 volts. And everything that we compare in terms of electrical potentials of different types of half equations are relative to this reference potential, which is the standard hydrogen electrode potential, which is 0 volts. Everything else is measured relative to this, right? So standard hydrogen potentials. Now, as I said before, the theta in the in the electro potential marks that the electron potential is measured under standard conditions, which are 298 Kelvin temperature, 100 kilopascals pressure, and a concentration of 1 mole per dm cubed of any solution. Now, for the standard hydrogen electrode, that's 1 mole per dm cubed of H plus. But even now, going back to this, for all electron potentials, now going back to this original equation here, it's 1 mole per dm cubed of all solutions. So if you have a mole of, let's say you had Br2 or bromine solution, right? Or bromine water, it would have to be 1 mole per dm cubed of of bromine. Or if it's Br2, it technically would have to be 0.5 moles of Br2, I guess. And that's quite important to understand here, that it's a concentration of 1 mole per dm cubed of any solution. It's important to use the standard, and it's important to use these standard conditions for reference, because changing any of these factors would change the potential and give you a different answer. So if we have a standard potential, right, of I don't remember the specific standard hydroelectric potentials, but say a usual, in terms of the reference book, of a standard electric potential is 0.55 according to the reference book. But let's say you use 5 moles of Br2, right? It will no longer be 0.55. It will be a completely different value, because you have a completely different solution. The concentration of your solutions the concentration of your solutions here are really what cause it determines where oxidation, which electron is being oxidized, which is being having reduction, and the rate at which is happening as well. And that would also dramatically affect the electron potential. So it's important that we maintain standard conditions, so that we can able to use it as a reference to say all the values that were measured for the standard electron potentials were measured according to standard conditions under these same conditions and references. The same reasons why we have it's a control variable. That's what it is. All it is just a control variable. That's all it is. It's just a control variable. Anyway, that's it for this video. Hopefully I wasn't talking too much, and hopefully I wasn't confusing you any more than I did originally. Hopefully this video was helpful, and more videos will come about me doing actual questions and examples, so you can see what I mean when I say these things. I promise in the long term you will get this topic.